Alright, so now for section 2.2, it's a section on functions. I need to, clarify a few things here. A lot of this section will be vocabulary. So first off, we see two definitions. First definition is a relation. A relation is just a set of ordered pairs. So for instance, this set, remember braces means a set. So in the set we have this comma separated list, and each thing in the set, each element of the set is an ordered pair. 2, 3, 5, 6, 0, 7, and 2, -1. So this is a relation. I'm calling the set R for relation. Okay, it's fairly straightforward. This is where things get a little more complicated. A function, now, is a relation where each x value corresponds to exactly one y value, meaning there are no repeats in x value. So an x value will only have one y value it corresponds to. If it had two y values, then you would see a repeat in x. For instance, here and here. So the x value 2 doesn't correspond to only one y value, it corresponds to two y values, 2 and 3 and 2 and -1. So this relation is actually not a function from the previous example. Okay. Very often, by the way, we call x values inputs of the function and y values outputs of the function. So really nice diagram here, I think, to help you remember what's going on, is a function is treated as like this mathematical machine where you plug in x values, so those are your inputs, and you get back y values, your outputs. The only thing is, this machine can't make any decisions. It doesn't handle ambiguity very well. So if you were to plug in 2 and it has this in its coding, or however you want to put it, you plug in 2, it doesn't know what to give you. It would have to make a decision. Does it give you 3? Does it give you -1? It wouldn't know. Very often, by the way, there are these diagrams that are used with functions with arrows. So you'd have x values and you would have y values. So for instance, here the x values are what? Let me write them in order. So the x values in order are 0, 2, and 5 in order. Now remember, this relation is not a function, so we'll kind of see why with this diagram. Okay, the y values in order, -1 is the smallest, 3 is the next one in line, then 6, then 7. Okay, so now what goes to what? Well, 0 arrows to 7. This is sometimes called a mapping diagram, so 0 maps to 7, 2 would map to 3 and also to -1. And 5 maps to 6. How you can tell this is not a function for sure is that this is the culprit. 2 maps to 2 different y values. So it falsifies this, doesn't satisfy that every x value corresponds to exactly one y value. This x value corresponds to 2. So we kind of see why there. That's good. So next I want to describe something that is true for functions and relations. Now notice, based on this language here, every function is technically a relation because it itself is a relation. But not every relation is a function, as we saw from this example. Okay? So what I'm describing here is true for relations, meaning relations and functions, because functions are relations. Good. So for domain is the set of all x values of a relation, where the range is the set of all y values of the relation. So here, the domain would be the set of the x values 0, 2, and 5. Just that set of those numbers. Okay. The range would be -1, 3, 6, 7. Great. So the nice thing about points, though, is you can plot them on the xy plane. So there's a nice visual representation of relations. So here, two relations. There's infinitely many points, so it's very difficult to write it like this. There are equations that correspond to these, so I can get into that in a second. We could take advantage of set builder notation. But for right now, I just want to talk about the domain and range of these things. So of course, this circle here has what domain? What are the possible x values we can have? Well, one nice way to visualize what the domain and what the range are to look at the shadows of the x and y values of the graph. So in this case, if you look at the x shadow, this will correspond to all of the x values that you can possibly have. In this case, It's the interval negative 2 to 2. Every point on this circle has an x value that's in this interval. Either it's between negative 2 or positive 2. So it could be equal to them. So like this point, the x value is negative 2. This point up here on the circle is some x value that's in between negative 2 and 2. And then it ends at positive 2. And you can't go beyond that because you'd be outside of the circle. You wouldn't be on the circle. Remember, we're looking for points on the circle. Similarly, what do you think the range is? What do you think the set of all possible y values for this circle are? So we would look at the y shadow, and the y shadow in this case is also the interval negative 2 to 2. Now it's of y values, but we can still write it in interval notation. So it's negative 2 to 2. Okay, great. All right, now what about this parabola here? Well, this downward parabola, the set of all possible x values is kind of funny because it's the whole x-axis. It is indeed the whole x-axis. As it turns out, parabolas, they spread out indefinitely. So if it was up, it goes up indefinitely and opens wide indefinitely. Same thing for going down. So even though it may look like it curves down like this and continues vertically, it doesn't. It actually goes like that. It's wider and wider and wider as it turns out. Okay? So the domain is actually the whole x-axis. So the way we'll describe that in interval notation is from negative infinity to infinity, which you should like based on our discussion from 1.7, right? Right. And what about the range? Well, the range goes from where to where? Where do the y values go? Well, the y values actually start at 1 and go down to negative infinity. So the lowest the y values can be are negative infinity, but the highest they can be is 1, and it could be equal to 1 because there is a point that has a y value 1. So namely, the range is the interval negative infinity to 1 closed on 1. Great. One last thing I want to say here before I move on to some more things about functions is, well, if you look at this, it's kind of hard to tell. But let's consider this point that I plotted and this point down here. I'm trying to make it so that they have the same y value. Notice that it's totally possible that these two will have the same y value. Sorry, not same y value. I meant same x value. So they definitely have different y values, but they have the same x value. I misspoke earlier. Sorry about that. But yes, these 2 points have the same x value but different y values. In other words, it's this scenario. You have one x value that corresponds to 2 y values. So just by speculation, just by looking at this, we can tell right away that this is not a function. This is not the graph of a function because you have 2 points that can have the same x value but different y values. Here, it's not the case. Any x value would only correspond to one y value. And you can see that visually by picking just some random x value, projecting it to the graph, and it only hits the graph once. Here, pick any x value at random basically, and it actually passes through the graph twice. 2 different y values. So here this is a function, where here for the circle it's not a function. The graph is not of a function. Alright, so yeah, so we're going to do some more examples right now, and we'll talk a little more about this phenomenon, and we'll describe the generalization of that. Okay, so generalizing what we saw earlier, this is what is called the vertical line test, or VLT for short. And it says the following. It says that any vertical line can pass through the graph of a function at most once. Meaning you can tell if a graph is a graph of a function just by passing a bunch of vertical lines through it to see if it passes through more than once. Here, for this line with positive slope, passing any vertical line through this only passes through or intersects the line once each. So this is a function. So I'm gonna write a let me write a smiley face for function, and then I guess a sad face for not a function. Here it's also the case, even though it's really, really curvy, it's also the case. Any line, any vertical line you pass through the function, the graph of the supposed function, only passes through it once, and it is not a function. If you take a look at that circle we saw earlier, passing a line through almost any x value along the circle passes through the circle more than once. Okay? Here, this vertical line, for instance, passes through twice, so this is not a function. Notice this was a function, but this is not a function. Also, I say at most once. Can it pass through 0 times? It certainly can. For instance, let's say this lower half of this sideways parabola wasn't there. If the lower half wasn't there, then we wouldn't have this second mark. So it would be a function in that case. And this line would pass through the function 0 times. So passing through a graph 0 times is okay. Once is okay. More than once is not okay. That's why I say at most once. Okay? Here, this is good. This is good. This is good. This is good. Anywhere through the loop is bad. In this case, it looks like it actually passes through 3 times, which is like extra bad, I guess. Good. So function, function, not a function, not a function. Good. So now we're going to move on to the most useful thing in this section, which is function notation. And the function notation we want to establish is the following. Y is equal to f of x. So algebraically, given an equation of a relation, remember a relation is a set of ordered pairs, and ordered pairs are solutions to an equation in 2 variables. Great. So if you can solve for y completely, and you get y by itself, and you don't have any plus or minuses or anything like that, then you can without certainty say that it represents a function because every x value will correspond to only one y value. And let's see what I mean by that. So here, y is by itself already, so we can replace y with f of x. And that's using our function notation. And notice, anything you plug in for x will only correspond to one y value. It's kind of a little hard to see, but with the next problem you'll see it for sure. So this next one, there's a square in y. So if we wanted to get y by itself, what do we have to do? We have to subtract x squared to the other side first. And then we'd have to finally square root to get y by itself. You square root to undo a square, sure. But what happens when you square root both sides of an equation? What do we learn from 1.4? The square root property, right? You get a plus or minus on one side. So on the left, yeah, they cancel out, that's fine. But on the right, so you just get y on the left. But on the right, you get plus or minus radical 4 minus x squared. So this, as it turns out, is not a function. So I'll write a sad face and I guess a happy face here. And we can tell because almost any x value you plug in, you'll get 2 different y values. So if you plug in x equals 1, for instance, you'll get 1 squared is 1, 4 minus 1 is 3. So y would be positive radical 3 and negative radical 3. So there are 2 y values that corresponds to that one x value. Also, if you don't believe me, this graph right here, y squared plus x squared equals 4, is just the graph of a circle. It's the equation of a circle with radius 2. The exact same example we saw earlier, we already said that that wasn't a function. So this better not represent a function as well. Here there's a power on y, but it's an odd power, so odd powers are actually okay, believe it or not. We haven't seen too much of this, but as it turns out, when you cube root both sides, and this is only because 3 is an odd number, they still cancel out on the right, on the left, but on the right, you do not get a plus or minus. You only get a plus or minus when you have an even root. If you have an odd root, there's no plus or minus. So there's no decision making here. The plus or minus, there's an or, so there's decision making. Here there's not, so we can replace y with f of x because this is the equation of a function. So how do you utilize function notation? You get y by itself. If you have no plus or minuses, then it's a function. And we can actually evaluate y for any x value. So we'll see that right here under evaluate. So to evaluate a function, I'm going to say the following. Let's say this is the graph of a function. Notice it looks like it passes the vertical line test, so let's assume it does everywhere. Let's denote it by f for function. That's the notation here. By the way, you can also commonly use G, H, K, any letter really as long as it's not already taken. Also doesn't necessarily have to be of x. There's an example in the, well, I guess a homework problem in the book where they give you g of t. So here our variable is x, but in that problem the variable is t, and they're using labeling g for the name of the function. I'm using f here though. Anyways, regardless of the letters you choose to use or whatever the book tells you to use from the homework problems, let's take a look at this. Oh, by the way, from a graphical perspective, this point, if this is a point on the function, then its y value is f of that x value. This x value is a, so its y value is going to be f of a because of this, because of our notation. The y value is equal to f of the x value. So we'll see that here. We have this function given to us. They say f of x, so it's assumed to be a function already. F of x equal to 4x squared minus 3x plus 5. We want to find f of 2. So all we're going to do is plug in 2 for x. Anywhere we see an x, replace it with 2. Fairly straightforward. Notice this reduces some of the language. So instead of calling this y and saying find y when x is 2, just call it f of x and just say find f of 2. It's a lot easier to say that. Rolls off the tongue, I guess. So plugging 2 in for x, we get 4 times 2 squared minus 3 times 2 plus 5. Good. So I don't have too much space, but let's see. 2 squared is 4. 4 times 4 is 16. 3 times 2 is negative 6. Well, negative 3 times 2 is negative 6. Plus 5. So 16 minus 6 is 10. 10 plus 5 is 15. So f of 2 is 15. And that would correspond to the point 2 comma 15. Just like this corresponds to the point a comma f of a. Just to kind of put it together. This is going to be a little more complicated, to be quite honest. F of x minus 2, we're going to do exactly what we did over here. This is our x value. We replaced every x in the equation with this, with 2. So we're going to do the same thing, only it's an expression we're plugging in for x. So you have to be careful, but let's see. I'm going to write it down below. And it may simplify, but let's see. We get 4 times x minus 2, all squared, minus 3 times x minus 2, then plus 5. So there's a lot to do here. I need to expand things out and distribute this negative 3, and then possibly combine like terms. I may not have space. I mean, let me shift this down a little bit. But anyways, let's start simplifying things. So distributing the negative 3 gives us negative 3x plus 6, and then plus 5. Here, x minus 2 squared, we've seen this before, it's a binomial squared. So the 4 is still going to be on the outside. But this binomial squared, we know how to do it. It's the first one squared, so x squared. 2 times their product, so it's negative 4x. The last one squared, negative 2 squared is positive 4. Distributing this 4, combining these two, will give us plus 11. We have the negative 3x in front of that. And then here we get 4x squared minus 16x plus 16 after combining. We can combine a little more. 16 and 11 are like terms. Negative 3x and negative 16x are like terms. And I think we have space here. Let's see. So altogether, after combining like terms, we get 4x squared minus 19x plus 27. You see that? Yeah, I believe that makes it on screen. Perfect. Good. The next one is a little less work, to be quite honest, but let's see. F of x is just what it was. 4x squared minus 3x plus 5 minus f of 2. We already found f of 2. What was f of 2? F of 2 was 15 minus 15. These combine to negative 10. So altogether we have 4x squared minus 3x minus 10. Fantastic. That concludes 2.2. So I'll see you in the next video for 2.3. Thanks for watching.